This video aims to give you a very brief introduction on Young, how to get started on a supercomputer for people who have no background at all, as well as maybe some slightly unusual features of Young that will benefit people with maybe some more experience of using supercomputers. Now, the online pages from UCL are extremely good. If you actually want to get started, they would be the best place to have a look. It talks step by step with guides on how to get started for people who have experience, people who haven't as well. There's a kind of beginners area. But for those of you who prefer videos, the idea of this video is really to give you a kind of slightly more vocal and visual introduction. This talk is based on one I gave at Brunel back in October, and it was open to other consortium members. But the idea here is that this video can then be made available as an introduction to people. Now, the plan is for us to put together a range of other videos. And so if anyone has suggestions for particular areas you'd like to see additional videos, then I encourage you to get in touch through the website, and we can look into doing that. Okay, so the plan today is to give you an overview of Young and the MMM consortium, talk about what a supercomputer is, and this is via talking first of all about what a computer is. So I'll actually talk a little bit about hardware in general before going on to say actually what's different about a supercomputer. Now, the reason for covering this basic information is because some people, typically users who have only really used Windows and very small kind of cases, typically have this idea that you can just make jobs faster on a supercomputer, and you can run programs such as, say, MATLAB or ANSYS, and just a supercomputer is just a bigger computer. Now, that's true, but a little bit of understanding about the hardware will inform you about which problems are amenable to supercomputer time, and also the limitations of that. Now, to get started, we need to create an SSH key and an account on Young, and each individual partner will have a different way of doing that through their contact person. So if you don't know who your contact person is, go to the Young MMM website and you'll be able to find them on that, and then you'll be able to get in touch with that contact person, who will then be able to submit an account request for you. And the account should be open to everyone at your institute, but different institutes have different systems, so you'll have to talk to your contact person for that. I'll talk a bit about logging in, building a simple example and running it, and I'll try to give you a kind of quick demo of that using my own code, which is a molecular dynamics solver. This is a bit of code that I build myself, so I'll show you the steps involved in doing that. And I'll also talk a bit about how you can actually use existing codes, which are slightly more user-friendly, especially if they're already installed on the module system. If they're not, then I'll talk a bit about how we actually submit new tickets for new programs. And then finally, we'll talk a bit about logging in from Windows, various strategies for that, and the best one for you will depend on your experience with using these types of things. And then for the end of this particular video, I'll finish with some best practice use on a supercomputer and talk a bit about gold time. Again, this should be gold time in general, not just our gold time, but each university will have their own gold time. Okay, so the overview of the Materials and Molecular Modelling Hub is a consortium of 12 universities. It's in its second phase. So the first phase was actually a subset of these universities. It included a few other partners. And the idea here is these universities come together to work through a shared supercomputing resource, originally called Thomas for the previous research, now called Young. Now, this supercomputer is actually hosted at UCL, and they built and host a supercomputer. They do a brilliant job of keeping it up and running. There is money within the consortium for that. The supercomputing grant pays just for the hardware, and then each of the partners of the consortium pay towards maintaining that supercomputer. Now, in exchange for paying towards the maintenance of the supercomputer, each of the consortium members gets a share proportional to the amount of money they put in of the time on the machine. Now, the idea is of these tier 2 machines that EPSRC have funded is that 70% of the time goes to the contributing partners who pay for the maintenance, 30% is open to ballot systems. And so in order to basically apply, if you're not part of the consortium, you'd have to apply for the ballot. So if someone's watching this and they want to know how to use this, and they're not part of the the partners network, then they can actually apply for the supercomputer through a ballot system. Now, the mechanism for partners to use this 70% time is gold. And I'll talk more about that towards the end of the end of the presentation here. Okay, so the distribution of partners is shown on the left here. You can see it's a number of universities dotted around the UK. Now, part of the MMM hub is, although this is focused mostly on a supercomputer, it also has strong links to a number of other consortiums for computational chemistry. So Materials Chemistry Consortium, UK Car Parallelism Consortium, and then the High-End Computing Consortia, as well as the Thomas Young Centre, which is the kind of London-centric institute for kind of computational chemistry. But generally speaking, the scientific areas have actually expanded beyond that. Myself, I'm actually more on the kind of continuum fluid dynamics molecular end. Certainly, I would say most of the partners are more on the quantum side of that. But the idea of this computer is not simply just computing resources. It's also an opportunity for us to collaborate, to build collaborations across the network, and also to get involved in both scientific dissemination as well as computational sharing. So again, as part of this set of talks, we aim to actually put together research talks on particular software. So again, please, I encourage you to contact me directly if you would like to give one of those talks, if there's a bit of software that you develop or use and would like to talk about, especially if you're doing it on Young, then that would be very useful. Okay, so let's start. How a computer works. So on the left here we have a computer with the side taken off, and you can see, let's start with the obsolete bit, the compact disk drive, which is pretty much not going to be included in most computers of the future. We have the power supply here on the top right hand corner. And then the key bits of your computer is a CPU, which is attached to a motherboard. So this big bit here is the motherboard, which essentially is most of the kind of guts of the computer. The CPU with the fan sitting on top here is the thing that does the computations. RAM is essentially random access memory, that is the memory that your computer CPU actually uses, kind of like short-term memory. So it's the part of memory that is directly accessible and only exists for the period of running of a program. And then we have hard drives, and hard drives, everyone is quite familiar with this, the kind of long-term storage. These are things where you store your pictures, you store your program, you store your data. So the way a computer works is essentially you have a couple of numbers, for example, stored in memory. Now these could be stored on a hard drive. For them to be used in a program, that would then need to be loaded to RAM. This RAM is then directly accessible to the CPU, and there are various levels of this which have different access time requirements. But from our point of view here, you can think of a computer basically doing a process of loading, say 2 numbers from memory, doing an operation on them, a computation, which in this case is just adding those 2 numbers together, and then storing the result back in memory. So you can see here there's kind of load operation, there's a computation done, and then a save operation. And so this is stored then in RAM, and then when the program finishes, potentially it could be stored back to a hard drive. So this is, pretty much the basis of all modern computing, this kind of process of loading and then saving. So the difference here now for a supercomputer is it's lots of those individual processors joined together through high-speed interconnects. And so there's a few important things to understand about this. The first is that each node has its own memory. So a node on a supercomputer you can think of essentially being like a separate computer. So if you think of a supercomputer as lots of computers connected together, a bit like the internet, a supercomputer is just using lots of those computers together, working collaboratively to solve problems. And what this means is you have to write your programs with the understanding of this kind of architecture in mind. So if I want to do a computation on my first node here on the left, on this computer, then I have to load the data from memory, I do the computation, I save it back. But what that means is that the computer here in the middle has no access to the memory stored on the computer on the left here. The only way it can get it is through exchanging information through these high-speed interconnects, or saving it to disk and loading it back up again. Now, saving to disk is extremely slow operation. So generally speaking, with your programs, you want everything to be done from RAM or through these high-speed interconnects. And so what this means is your entire program has to be written with that in mind. Now, Young has 576 nodes, each of which has 40 cores. Typically speaking, your job should be between about 3 to 5 nodes in size. The minimum job size is 40 cores or 1 node. And the idea here is that really you should be using at least a couple of nodes, and you should have your code written in such a way that it can use interchange of data between those different nodes. So this, really shapes the way you should be thinking about running jobs. Now, the 3 types of parallelism that exist, and to a large extent, you may not need to worry about this if you're using existing codes that have been written with this in mind. But generally speaking, any code that you're using, especially open source code, which are the predominant software on Young, and especially research software, has been written with this kind of parallelism that is apparent to the user. So it is important to understand the kind of limitations of this. The first type of parallelism is OpenMP, and this is basically what's called threaded programming. So the idea is within a particular node, you can actually run your different calculations in parallel. So the typical unit of computation would be, say, a for loop, where you kind of loop 40 times, for example. Instead, what you can do is split that for loop into 40 threads doing the job individually, and so you could get it 40 times faster. So rather than waiting for one CPU to basically loop 40 times, each of them can take part of the problem. And this is what's called a shared memory paradigm. So it means it requires basically the programs to have access to shared memory. And there are some supercomputers built with very large numbers of CPUs connected to a single big block of RAM. Now, Young is not that type of computer. And so in order to get efficient operation of large-scale jobs on Young, you need to be using a distributed paradigm. And the most common one is used through what's called the message passing interface. So this is what's known as an API that essentially standardizes the exchange of information. Essentially, it allows information exchange between the different nodes. So for example, if this node knows part of the problem, it would have within its code MPI send that would send some information to this. And this would solve maybe a different part of the problem, and then MPI send to this part of the code. Now what this means is you have to rewrite your code with this kind of limitation in mind. Now this normally in a kind of typical example, if you're solving for some scientific domain where you have, say, molecules, and these molecules are being solved, each of them individually being solved, you would split your domain up across the different processes. So for example, this may be node 1, this would be node 2, this would be node 4, and this would be a different node. Now bear in mind, each of these individually are separate memory, which means the exchange of information then has to occur at the boundaries between them. And so this is typically what's done in this kind of distributed paradigm. Now, one thing to bear in mind here is actually, although I've written nodes here, typically the actual terminology that's used is each of these is a process. So this process here would be a single core, for example. Now, although these have access to the same block of memory, typically it's more sensible to actually write your code in such a way that each core has its own access to its own block of memory. And so what that means is that typically you'll see very good scaling within the node, because all 40 of these cores, although they have their own separate memory and exchange information, the exchange of information is very, very quick because it doesn't require connection through a kind of interconnect. However, this does then mean that when you go to, say, two nodes, the code is identical because you've essentially treated everything as individual logical units that have their own individual memory. And the only interchange of information is through these message passing operations, such as MPI send and MPI receive. Okay, so that's the main paradigm, and most of the code you use on Young should be of this form. The final form of parallelism is what are known as job arrays, and these are batches of individual runs, or what's known as high throughput computing. And in this example, you would have a set of runs that do not depend on each other. This is often referred to as embarrassingly parallel. The idea that you can essentially have 40, 80, in this case maybe 120 independent jobs, and you can submit them as a job array, and each of them will run on their own individual core, and then the results of each of those jobs can be saved to disk. And those type of jobs again are ideally suited to parallelism. So both MPI and job arrays are fine. OpenMP the limiting case is you basically can't run it past a single node of 40 cores. It's worth mentioning here, by the way, that there's hyperthreading on each of the cores. So although there are 40 physical cores, there are 80 virtual cores. And so you have to basically be aware that sometimes it might be faster to actually make use of this hyperthreading. In all cases, it's worth testing this out to see. So to give you a bit of technical specification, it's 23,000 cores of Xeon Cascade Lake cluster, split into 5, basically distributed over 576 nodes, each of which are 40 cores with the 2 hyperthreads, which make them kind of 80 virtual cores, 40 physical cores, 192 gigabytes of RAM per node, and it's diskless, which I'll talk about what that means in terms of your job submission scripts, but generally this means all writing will go straight to the kind of shared disk. There are a couple of larger memory nodes, anyone who needs to do 1.5 terabyte or 3 terabyte simulations. So these are the type of jobs where, you know, your actual your jobs are extremely large and you need more RAM. Now these are organized into 36 node compute units. And so what that means is the interconnects that we talked about being high speed, let's just go back to this slide, are basically the high speed interconnects are between these different nodes, and then between those compute units, essentially the interconnects will be much, much slower, which means for scaling, you would expect to see up to say 36 nodes that are on the same CU, good scaling, and then outside of that, you would see a sudden large drop in scaling, which means any scaling test you do above 1,440 cores, you would expect to see a drop off. And if you don't insist that they actually are all part of the same CU, then again you might see a drop off. So just bear that in mind for scaling tests. There's 1 petabyte of luster, which can be written to at 8 gigabytes a second, and it's in the data center at UCL. So we've had a little while since, you know, we've come out of lockdown, at least at this time of speaking, but UCL managed to get this supercomputer up and running during the kind of first lockdown, which was absolutely incredible. You know, and is operating ahead of schedule, or at least ahead of when we expected. Okay, so the way you create an account and give your SSH public key will be dependent on whoever administrates your local access, and you will send this most likely once you've signed a form to whoever it is creates the account. Now, one of the questions that comes up quite a lot is, can you have separate additional keys on here? And you can do this once you've logged on. So the advice is to choose the computer that you have, you know, the most natural access to, or one that you'll definitely have access to create the initial public key. Once you've created that account, you can then add additional keys. The other possibility is you can copy your private public key pair from one computer to another. Now, there are obviously security implications of that. If your private key gets compromised, then every computer you own will essentially be accessible. So the advice here is to always use a password with your key pair. You know, and that's kind of true. You know, both on your kind of first computer, even if you have it on just one single computer. Okay, so to log on, you use the command of the form SSH. Optionally, you can put X forwarding, so this allows you to have graphical user interfaces. Your username, which will be the one assigned to you when you create your account, and then the network address of Young. So everything on a network is given an IP address. These IP addresses can then be given aliases. So you can think of it as a bit like a website, where, you know, this is actually the IP address of the computer, but, you know, written in a human readable form that's then directed to that IP address. Now, what I personally do is just create an alias in my .bash RC for anyone who uses Linux or Mac. We'll talk a bit about Windows in the next bit. And this would be of the form, say, Young. So you can just type in the word Young, and it automatically does a command of this form. So it makes it very easy to log in. Okay, so to log in from Windows, you have a number of different options. I'll cover here the most common, which is PuTTY. There are a number of other clients that will allow you to log in. I'll also talk very briefly about a Linux subsystem, and that's actually going to be what I'll use to show you the example. Now, I would personally recommend a Linux subsystem if you're going to do any type of development locally, or you just want to test things out before using on a supercomputer. Now, in order to use PuTTY, you're best to go to the UCL website, which you can see on the screen. You can get this by searching for MMM Hub Young, or following the link on the sign up for your particular institution account. So essentially here we're essentially creating an SSH key with PuTTY, and then the process for actually creating that you can follow. You'll put the SSH key in here, copy that to the server, and there'll be the process of kind of connecting from that. So this is a generic guide that they've linked here, but it obviously will work for that. And in order to actually log in with PuTTY, you'll put in the host name and IP address there, as well as the username. And bear in mind it's SSH here. Now, I personally use what's called the Linux subsystem. You can install this again, like most things, by typing in into your search bar, and then this will give you a step-by-step guide for how to install this. It's fairly straightforward. The only thing you have to do is adjust a particular system parameter to allow this. And then once you've set that up, it works essentially like a completely self-contained Linux. So you create this terminal, and then you can use the command that we showed you in the previous slide. So this SSH, and then your MMM hub, as you can see here. Provided your particular account, public and private key, has been set up correctly, then it should log in correctly. Now notice it says permission denied here because my user account isn't MMM1234. My user account is A-list under Young. So for me, my account is 0719. So I can log in with this command here. And you can see that logs in and gets us the open page of the MMM hub. Now I'll show you actually an example of this in a bit. But so this for me is how I would suggest working on Windows. But obviously PuTTY is another option and works in the same way. Okay, so building or getting software. Now what I'm planning to do after this is to show you an example of building your own software and how to use that and submit that. There's also the module system, which I'll show you very briefly as well. But essentially this allows you to load pre-existing software. Generally you're only going to find open source software on Young, unless you have some particular deal. If you have a license, then it's possible you can discuss with either your point of contact or UCL directly how to allow that on this particular server. Generally commercial software will be per node. So what you see here is that the expense spirals quite quickly. So actually per node or potentially per core. And this is really where it becomes prohibitive to run on a supercomputer. So as I said, I'll talk about the kind of building from source very briefly. I think for most users this may not be a concern. Of course, people who run their own software, then they should know how to do this anyway. The module system you'll need both for building your own code to make sure you have the kind of libraries that you need available, but also to use existing software. And then any problems you have, you can email research support directly, or you can raise an issue on GitHub. I think both are equivalently well supported. Okay, so just to show you how we would Young. So this is basically a Linux interface. So for those of you who don't know Linux, my advice would be to look into Bash and just some basic commands in Bash. You've got your ls to list what's in a directory, change directory, cd you can change, and then cd double dot to go back up a directory. Present working directory is done by pwd, and that will tell you where your current directory is. So this is like a Windows file browser of this type, but done from the command line. Now this becomes important because this is where you have your input files and where you kind of run the jobs and where you get your outputs. So to see which modules are available, as we've just been talking about, we'll do module avail. And you can see what this does is it lists all of the available software on Young. So these are also given on the UCL website, so you can pop over there and have a look at the list of software that's available. There's various paid for resources, installed software, and so on. And it will talk more about how you can use these. but you also have them within the modules here, and you can see. Okay, so when you can see the list of modules available here. Things like Abacus are obviously paid software, so they are available. You just have to maybe discuss use of those, and you have your open source software, things like GROMACS, molecular dynamics code, and you can go down and see all of these. Keras machine learning, LAMPS is in the MD code. And we have things like TensorFlow again at the machine learning platform. And there is a version of MATLAB on here for people who want to use that. Now, generally speaking, the advice would be to write the MATLAB code locally and then port it to the supercomputer, and make sure you're aware of how to run it in parallel. I think that's a completely separate discussion, but definitely something you should be aware of is that you shouldn't be using code here that isn't at least parallelized, as we've talked about with the MPI. The other code on here is OpenFOAM. There's a few different flavors of OpenFOAM here, and then obviously the quantum simulation tools, which I have to confess I'm not too familiar with, but Gaussian, I think VASP, and a variety of other tools for kind of material simulation. Okay, so that's basically how we load the modules, and in order to load the different modules, you would use a command of the form module load, and then you choose, say, a particular module. So, for example, if we wanted to load Eigen, which is tensor calculus, then we load that. And then if you do module list, you can see that Eigen now is included on that list of modules. And notice by default, the default compilers are MPI with Intel. So again, if you want to change those to the G-Fortran compilers, then you can do that using module unload and then module load. So these are sort of typical ways of kind of changing software, and the advice on the UCL website will give you insight into how to do that. Okay, so back to the presentation. The thing to bear in mind is that when you actually run your code, you should never be running any of the software directly on what's called the head node. So when you log into your Linux system, if you're used to running on your local computer, you just run the code. You compile it, or you just load something like LAMPS, and you just run it. Now, on a supercomputer, you should always run it by compiling it and then actually running it using a job script. Now, generally pre-processing, so this would be setting up a run, creating kind of your molecular structure, your material structure, your finite element setup, or whatever you wanted to do. If that's a fairly straightforward computation, you either do it on your computer and then you copy it across. Alternatively, you can actually do that on the head node, provided it's not computationally too intensive. Anything which requires MPI or is a large job should really be done using a job submission script. And then the post-processing, that's visualizing your results. You in principle can do this again on the supercomputer. It does have software for that, but again, best practice and consideration for other people dictates that actually if it's going to be anything more than a kind of quick plot, really you should be copying the data back to your own computer and analyzing it on your own computer. With that in mind, it all depends on your use case. If it's gigabytes of data and you want to have a quick look before you delete it, versus extensive analysis that you need to run lots of computations on, that will dictate whether or not you use it locally or in situ. Okay, so a job script we'll talk about in the next slide. But the idea is that you're submitting that you want to use this much resource for this length of time, running this particular thing, and it's put into a queue, and as soon as the resources are available, based on whether other people need it and whether or not you've run too many jobs recently, kind of fairness allocation will determine whether or not your job is run. So the other factor in this is that you can choose which queue you use. Now, each university that's contributing funds to the project has got an allocation of what's called gold time. So this is priority job submissions that put you higher up in this queue. And then your free or test jobs, will not actually take some of your allocation of time, but essentially will queue for longer in principle. Okay, so this is a typical job script. Again, it's lifted from the UCL example guide, and you can see here on the left hand side you've got example job scripts. We've got our different types of jobs, as we said, the MPI job, which is the multiple nodes running in parallel, and then this array job submission. So this is if you have lots of jobs running individually on lots of different cores. These two have different job submission scripts, so you can download these. The multi-threaded should only be run within a particular node. So your size limit here is 40 cores, 80 with hyper-threading. So again, make sure you tailor this to the architecture of the computer that we talked about before. Just to quickly talk you through how this works, at the top here we've got both the allocation. So you say that you want gold allocation, and then you specify this is your project allocation. So for me, I'm from Brunel, that would be Brunel allocation. For your particular institute, you have to check with your contact person what you should be putting here for your allocation. The alternative here is you could put free and use the free queue. So these first two here will determine the parameters of the run and which account, if you like, it's taken from. The rest of it is a fairly standard job submission script syntax. I'll run through very quickly. This is the wall time. That's the length of time you run on the computer. The maximum you have here is 48 hours. This is saying I want to run it for 0 hours, 10 minutes and 0 seconds. This is a kind of test job. You go to 48 here, 0, 0, 0 for the full longest time you can do. You can also request memory, and this is memory per core. Now, generally there's some advice online on how to actually choose the amount of memory per core, and there's some kind of scripts for doing that. Generally speaking, this is something you can test and just do a smaller job on your local computer before running here. Please bear in mind this is RAM per core. You've got 40 cores per node, so just make sure that this isn't a number in total that's larger than the amount of RAM per node, or your job will never run. It will just queue, or potentially. Now, the general advice on the Young website is that you actually need a temp directory. In this case, there's no temp directory needed. The job should run directly on Scratch. I'll talk a bit more about that. You specify the name of the job, so this is just purely for the naming of the output files you generate, as well as when you look at the queue. And then you specify the number of processors. So this example here, I'm using 40 processors, which is essentially one complete node of processors. You then specify where you want to run your job. So in this example, it would be a home. My ID, which you saw already, was MMM0709, I think. But you replace that with your own ID, and then Scratch, which would be the directory, which has additional storage where your outputs can go, and then the name of the output folder. The actual run itself is slightly different from other computers for those of you who are used to running on other computers. Instead of MPI run or MPI execute, here we use GE run, which is just a wrapper that deals with the machine file and the number of cores. And a number of cores will then come directly from the amount or the number of cores you've allocated. So yeah, just make sure you use GE run unless you know what you're doing essentially, or you'd like to kind of write in the machine file yourself. And then you specify the location of your simulation. Okay, so just a quick word on how you actually estimate how big a job you need. The answer is to test with lots of short runs, and it's well worth spending a bit of time initially to work out a kind of sweet spot for efficiency. And then once you've got that, you can essentially run jobs much quicker. If you spend a couple of hours working out the best possible run time, often you'll then run a case for maybe weeks, months. So it's well worth spending that time initially. Bear in mind that the minimum unit of computer usage is 40. So if you only request one single core, you'll take an entire node, and 39 of those cores will be doing nothing. So just make sure in whatever you're doing that you're actually using as much of the resource as possible. Also, there's this concept of hyper-threading, so it's well worth checking whether or not if you use hyper-threading, you actually get the benefit. So an MPI job with 80 cores run on one single node might actually end up being more efficient, say, than 40. Alternatively, the code itself might make use of hyper-threading internally. So, play around with that and just make sure you test what works better in terms of hyper-threading or not. You can switch on hyper-threading with a number of threads. So MP number of threads here will determine how many threads. So for example, if you want to set the 80 cores, it will be, you know, MPI 80 with that particular thing, but it's actually 40 threads. So just bear in mind that, you know, you can specify this you know, granularity, if you like, between hyperthreading or not, and try this out and make sure what you're using is the most efficient for your particular case. As for RAM per core, can't exceed 192 gigabytes. There are also some cores with more RAM if you need those for particularly big jobs. 192 gigabytes is massive, so it'd be very unlikely that you're going to exceed that if you're just a kind of typical user. And then generally you can profile your code using user bin time to look at your program and see the kind of maximum memory requirements if you want to get an idea. Yeah, and then just finally this allocation of gold time. You can check how much you've got, and it's topped up initially on the 1st of October, and there's more gold time released periodically. So, you know, I think your contact person, you can ask more about this, but generally speaking, this can be sub-allocated to groups. It could be allocated to individuals. It will be done by your own institute's policy. But it's worth being aware of this, because if you are using very big jobs and you're using up all of your university's time, it means no one else can. But similarly, also, if your university has allocation gold time and you're not using it, then you ideally should be, because this is important to show the people in your institute who are paying for this that it's a useful resource. Finally, the other things to bear in mind is the free and test queues. So if your gold run out, or you have a job you don't care about if it queues for a couple of weeks, then stick it on the free queue. And then for small jobs, short and small jobs, test queue is ideal. Okay, so the last thing I want to show you is basically how I run an example of my code. So we open up an example of the Windows subsystem. I use my alias Young, which, as we said before, just calls that SSH command, and we log in. Now, my particular job is actually saved from scratch. My code is Flowmile. Now, what I originally did is I actually, if we do ls, tilde is the home directory, and actually I saved under, I have my source code I actually checked out from GitHub. So originally I checked up a version of the source code from GitHub, and you can see this is written in Fortran. It has a series of Fortran files, and so essentially what I do here so for some reason this is remarkably slow. So this is a git checkout file. So for me, it would be make p, which makes the code, and I've specified on this that I want it to be built using Intel compiler. Now, bear in mind that the default is Intel. If you actually want to compile your code using, say, G-Fortran, and you need to use a different set of compilers. If your MPI version, you want OpenMPI, then again you can switch to that. As far as I understand, the Intel MPI is based on MPI CH. So again, just make sure your code works with that particular version. Now for me, what this does is it creates an executable, parallelism.exe. So that's what the make file does. I then copy that make file, that executable file, to the scratch directory. Now the scratch directory is where we're going to run our particular code, and I have a directory Flowmile here. And so what I put in here is just the executable itself and my input file, and then I have my run script. So what I want to show you is just the run script. It's of the form run script.sh. So you can see here we have the fact it's a gold allocation. For me, it's the Brunel allocation. For you, it will be whatever your institute's allocation is. I've requested the maximum time here, which is 48 hours. I've requested 2 gigabytes of memory per process, which is still under the 192 gigabytes per node. So it's 40 times this. So I'm requesting about 80 gigabytes per node. At the moment I'm still testing this out, and I'm running on 120 cores. So that's essentially using 3 whole nodes. And I'm specifying my working directory here is the same working directory that the run script is in. So this just lets it know to go there. And then my GE run command is using then the executable. So as far as I understand it, this working directory will be essentially where the code, the run script will go to before it starts running the code. And GE run here will then run my executable. And the syntax for my code is that the input file -I is that, similar for lamps or another MD solver. And then I'm using a restart file here, which is initial state. So that's it. That's how you kind of run a particular job. And then you can use the module system if you actually wanted to run another code. The module system you would use to load the particular executable you want. So for example, if I did module load lamps, I choose a particular version of lamps, which is 3rd of March one. So then sometimes you get this issue where it's asking for existing modules. So you follow the module advice. Let's try that. And it's now asking for plumed. So let's try that. So you can find generally, you want to kind of find the right selection of modules. Let's try loading lamps. Perfect. Okay, so now I've loaded lamps. You know that LMP MPI here. So this is the version of lamps that we have. So the executable that we've just loaded from doing the module load is LMP MPI. So let's take the example I want to actually run a lamps. So what I would do is I would go up a level. I would make a directory lamps run. I'd go into lamps. And bear in mind, lamps is just a code. You could this you can replace with whatever code you prefer to use. I'm going to copy my run script from here. So what I typically do is I look at the history set of modules that I've just loaded, and I'm going to add these to the run script. So we know before we run our job that we actually want to include those set of modules. So we copy those history commands, we get rid of the line numbers. And so what this means is in our run script, before we run the job, we make sure we've got all the modules we're going to need. And so we know now at the end of that run that we've got lamps. And so we have an MPI, and then this would be the input file. So we could take an example lamps input file. So for example, maybe the lamps benchmark. So maybe start with the lamps benchmark like that. And so there you have it. So that would be how you'd essentially run a version of lamps on 120 cores, at least initially. My suggestion would be to do this on a small test queue. So if we go up to the top, so I change this for test. I'd make this much shorter. So let's say 10 minutes, 2 gig, and we'll just lamps test. We'll do it on one single node, so just 40 cores, and this changes to the current directory, which we called lamps test, like that. Okay, so we just save that. So one thing to note here is that part of the reason you may not be able to see the cursor is because actually this is quite slow on my computer as well. And I think it's because the internet connection is either slow between UCL or someone is using the resources on the head node. So you might find this sometimes. And then in order to submit this, we do qsub run script like that. It's worth noting that I actually call it lamps run, not lamps test. So our working directory should be here. It should be lamps run. Run like this, and then we need the lamps benchmark file. So if we go to the lamps benchmark website, we can download the Leonard Jones benchmark. So we take the lamps benchmark, which is just that, and so we're going to create the lamps benchmark file. So we could paste the contents there. Okay, perfect. So then the one other thing to do here now is we want to specify that this is running parallel. So we just specify that it's going to be processed, and we want 40. So with 40 we can divide that, I guess, by 2, 5 and 4. Probably are more efficient ways to divide it, but that will do for now. Specify that actually, because we've got 2 processors in X, 5 in Y, 4 in Z. So we're actually modelling 32,000 per core. So it's an example of what's called weak scaling. Okay, so finally we're at the point where we can submit. We do Q sub run script like that. Okay, so you can see if you do Q stat, the job is queuing, and it's basically ready to run. So it's got 40 cores, it's been allocated that, and you can keep checking that to see when it's run. When it finishes running, it should then give the results in this particular file here. So that example may or may not work. I'm not sure. I haven't used lamps before on this supercomputer, but that hopefully gives you an idea of how you get started.